Hi everyone, welcome back once again. So let's continue calculating the wind load on our structure in the supporter frame. So we stopped at the stage when we calculated the QS, that's the dynamic pressure, and it turned out to be 2.12 kilonewton per meter square. Now we need to work up the external pressure, the internal pressure, and then find the net surface pressure, okay? But in order to do so, this is the equation for the external pressure, and you see we have the QS for both the internal and external, but there is two unknowns, the CPE and the CPI. There is also this CA, which is common in both equations. Now the CA is called the size factor effect. It's not a big deal, we'll deal with it later on, but the CPE and the CPI are coefficients, and we are dedicating this entire video and this entire part in order just to work out the CPE and the CPI. They are not difficult, but a bit lengthy, so let's get into it. Now we're starting with the external pressure. So remember, we are looking for the CPE, that's the external pressure coefficient. Now if I've got this building, okay, and I have the wind blowing up as seen, just remember the walls are going to have different pressure compared to the roof, okay? So that means we have to deal with the vertical walls separately. What I mean is that we find the coefficient for the vertical walls, and then we work out the coefficient as well, the external coefficient, but that's just for the roof, okay? So once we work it for the vertical walls and once we work it for the roof. Let's start with the vertical walls. The values for the external pressure coefficient CPE can be found in table 5 of the code, clause 2.4. Alright, so this is the table 5, and it shows the external pressure coefficient CPE for vertical walls, okay? Remember, we're not considering the roof right now. Okay, what it says basically, okay, you've got the windward front face, of course, and the leeward, the rear side of the building, and you have the span ratio of building, okay. What you need here is that, first of all, remember, when we are talking about wind, we have to consider, at least for this method, two directions, okay? 0 degree, this is the one we are starting with, and then we shift to the 90 degree wind direction. So starting with the 0 degree wind direction, basically I need the D and I need the H. Remember, the H is going to be 12 meters, whether I take it from this direction or from this direction, okay? Now the D, remember, D is a variable. If I'm considering this 0 degree direction, then the D is going to be in wind depth, that is 30, this one here. So I take the ratio, D over H, and it turns out to be 2.5. Now 2.5 is somewhere between, okay? That means I can go for the interpolation, linear interpolation, because the code also allows me to go for the linear interpolation. And as I explained before, we do it first for the CPE, the windward, the front face of the building. This is the front face of the building, the windward, and then we do it once for the leeward face of the building, okay? So for the first one, it turns out to be a positive 0.73, and remember, it's somewhere between these two values. And then we're gonna just negative 0.5 because nothing in between, okay? So that's it. We have the external pressure coefficient for the windward and the leeward, right? Remember, the wind goes also, okay, affects the side of the building, flows something like this, okay? So we have to consider the side face of the building. Now table 5 also provides the value of the external pressure coefficient for the side, okay, face of the building, but you have to divide it into zones, and in order to do so we need what's called the scaling length B, okay? Now why do I need the scaling length B is if you get back to clause 2.4.1.3, it defines the b, the scaling length, okay? It says the b, the small b, is going to be equal to the capital B, remember, the crosswind breadth, or 2h, whichever is smaller. I'm considering this direction, okay? The b is going to be 45, okay? And the h is just a constant. 2 times 12 gives you 24. So which one is smaller? 24. So I'm taking the 24 as my scaling length. The d, we're gonna need it in a bit. Okay, now I need to go to figure 12b. This figure 12b explains how to divide the side of the building. And that depends on the scaling length b and the d. Now, if your d is greater than your b, then you divide it into 3 zones. But if your d is less than or equal to b, you only divide it into 2 zones. So our case, obviously, the d is greater than the b, so we divide it into 3 areas. Okay, each one has its area. So if I'm calculating for a, then it's just 0.2b. That's 0.2 times the b, 24, gives you this 4.8 meters. We do it for the b as well, and then for the c. Okay, you got everything that you need here for the calculation. All right, so I have divided my side face of the building, and now I need to, well, if you check this table, you see it doesn't just provide the CPE for the side of the building. There's another column here. It says the exposure case. Sorry, it gives you 2 options: isolated or funneling. What do I mean by them? Now the isolated, well, as the name suggests, you've got this building, for instance, and there is nothing close to it. Isolated, okay? And you see, this is the windward face of the building, and the back is the leeward face of the building. This is the side face of the building. That's another side. Now you see the wind flows quite smoothly. There's no wind acceleration. If my case is isolated, if I'm talking about an isolated building, then I go for this column. But if I'm considering the funneling, well, then that means basically your building is surrounded by other buildings. It's like similar to this case. If I'm considering this building, okay, and you see this is the windward of the building, this is the side of the building, and you see the wind goes inside, like, it's not the same as if you treat the wind, the side of this building, similar to this one. That's because it gets narrow here, and you know the pressure is on increase. Okay, so well, this doesn't really explicitly explain the funneling effect, but if you get back to the clause 2.4.1.4, then it defines pretty well the funneling, whether you have to consider it or not. But for my case, I'm just going to consider my case or my building to be isolated. Okay, that means I'm taking these values in this column. Alright, now I'm assuming my building to be isolated. Right, if it's isolated, again, I defined my areas A, B, and C, already calculated from figure 12b. So I have the A, B, and C. Okay, what I need is just to find the CPE for each area. So for A, it's minus 1.3. For B, it's minus 0.8, and that's for C, minus 0.8. Sorry, that is minus 0.5 for zone C. This is not correct, okay? It's minus 0.5. Alright, let's move on, and this is just a summary of 0 degree wind direction. Okay, this is a 0 degree. This is the external pressure coefficient, windward, leeward, and the side face of the building. Right, we are done with the 0 degree wind direction for the vertical walls. Now we turn our attention for the 90 degree wind direction. Again, this was the 0 degree and this is the 90. it's exactly the same thing, except that when we are talking about the d, it's a variable. So d is the in wind depth. In this case, it's going to be 45. Okay, and if you get back to table 5, then again, that's the d over h gives you 45 over 12. It gives you this value. Go for the interpolation, find the windward coefficient for the leeward as well. Okay, and again, for the side face of the building, it's just going to be the same as for the case of 0 degree wind direction. So that makes it. This is the summary of 90 degree wind direction. Okay, and this is the summary of external pressure coefficients for both the 0 wind direction and for the 90 degree wind direction. Okay, this is for the 0 and this is for the 90 degree. Now we can focus on the roof. Okay, we're done with the vertical walls. Let's turn our attention to the roof. Okay, basically for the roof we do the same thing. We take it once for the 0 degree and we take it for the 90 degree. For the 0 degree, for both cases, we need to go back to figure 20. Okay, this is for the case when we are talking about the double pitch roof. Okay, that means we have to divide our roof into areas. Now this is for the 0 degree. Okay, and basically the figure 20 says that you have to divide it when considering the 0 degree into this shape. So we have the A, B, C, E, F, and G. And if you consider the 90 degree, you have to divide it into this order. Simple as that. Now for the 0 degree, you'll notice that we have the BL. And for the 90 degree, you might notice that we have the BW. BL and BW are both scaling lengths. Okay, BL is equal to L or 2H, whichever is smaller. BW has the same story, W or 2H, whichever is smaller. Depend on the fixed dimensions, not the variables. Okay, that's the L and W. And for my case, well, the L is going to be the same, 45, whether I'm considering 0 or 90 degree wind direction. And the 2H is just 24 for both directions. Right. My BL and BW, both of them 24, because in both cases they are smaller than the L and W. Right. Remember the angle, it's 7.6. We're gonna need it in a bit. Now for the 0 degree, this is the division of the areas. BL over 2, what we have to do here is just take the BL, which is 24 divided by 2. You get the area for A, the length of A. And for the side, it's BL over 10. Do this same thing. And that's how you divide the roof. So this is the building plan. Okay, we have the length of A and the width of A. For B, we have the same story. For C, this is not E, this is G. Okay, and we have the E, F, and etc. I've got all the dimensions that we need. Alright, now I need to get to table 10 of the code, and basically this is the table 10 of the code. For each angle here, you have a corresponding external pressure coefficient for the roof. Now we divided the roof into areas A, B, C, E, F, G. That's for the 0 degree, and A, B, C, and D for the 90 degree wind direction. What we need to do here is that we need to pick up the pitch angle alpha. So ours is 7.6, somewhere in between. That means we have to interpolate. Right, we're starting, remember this is not E, this is G. And we're starting with the A. This is the equation for the interpolation. And the external pressure coefficient, CPE, for A, remember 7.6 is somewhere in between. And for A, for the area A here, we have to do it twice. That's because we have a negative here and we have a positive here. Okay, so we interpolate once for the negative. This is the negative and this is the negative. interpolate, get the value in between. It's going to be minus 1.62. And we do it again once more for the positive. This is the positive and this is the positive. So we carry on the same procedure for A, B, and for C. For A, B, and C. But for E, F, and G, we only have the, as you might notice here, negative values. So we just do it once. And that's it. Now we have all the pressure, external pressure coefficient for the roof for each corresponding area. A, B, C, E, F, and G. Okay? Right. What we do now is just, as you might have guessed it, we turn to the 90-degree wind direction for the roof. And this is the division, okay, of the roof, considering the 90-degree. And if you get back to table 10, you'll see that all the external pressure coefficients are negative values. So, first of all, you divide the areas here based on the BW over 10, and then you have the area there. What you need to do is just work out, get back to table 10 and work out the CPE for each corresponding area. That's for A, B, C, and D. But here, remember, you have to do it only once. You don't have to do it twice because all the values are negative. Alright, that's it. Now this is for the 0-degree, the roof, okay, external pressure. And this is the 90-degree wind direction, the pressure coefficient. Right. Now we have all of them. If I want to show the summary of external pressure for both the walls and the roof, this is for the roof. Okay, let's start with the 0-degree wind direction. This is for the vertical walls, and this is for the roof. For the 90-degree wind direction, this is the external pressure coefficient for the walls, vertical walls, and this is the external pressure coefficient for the roof. Alright, now we are done with the external pressure coefficient. We turn our attention now for the internal pressure coefficient, and that is going to be well, much easier. Let's check it out. Alright, for the internal pressure coefficient, CPI, well, as I have told you, if I've got this building and, well, if I take cross section AA, this is the outside of the building and this is the inside of the building. If I've got this wind in this direction, then I'm creating, okay, internal pressure, because the wind can get inside, it traps inside the building, and I get this internal pressure. That is the positive pressure. But if I, for instance, shifted the door to the leeward side of the building, then I'm going to have a negative pressure. Okay? Now, the code has basically 4 categories. That is for the enclosed buildings, clause 2.6.1, and we have the buildings with dominant openings, 2.6.2, and then open-sided buildings, this clause, and then finally the open-topped cylinders. Now, the last two are none of our concern, at least for this moment, or this example. Though you might argue that the open-sided buildings, such as the ones you see here, might be used for the industrial purposes, but for our case, I'm not considering this. Okay, if you have the plan of your building, the elevation, etc., and you have it, well, permanently open, okay, one-sided open, then you have to consider this clause, and you have to refer to table 18 to get the internal pressure coefficient. My case is going to be within this category, enclosed buildings. So what do I mean by enclosed buildings? Enclosed buildings, basically any regular house with openings like doors and windows. And just to mention this, when I'm designing for the ultimate limit state, I consider the doors to be closed, but when going through the serviceability limit state, I consider the doors to be open. As I said, enclosed buildings are the most common types probably, and they have if you refer to table 16, where you can get the internal pressure coefficients for the for the enclosed buildings, you see that we have a positive pressure CPI 0.2, and we have a negative pressure as minus 0.3. This is the most common internal pressure coefficient that might be used by engineers. Alright, now if I'm talking about enclosed buildings, how is it different from the buildings with dominant openings? Okay, this is a building with a dominant opening. That means if I'm considering this case, this closed, that means I have to have an opening. Suppose this A, okay, this area of A, the opening, with an area greater than or equal to twice the sum of other openings. Okay, so that is B plus C plus D. B plus C plus D. If I multiply all of them by 2 and I get a value less than A, this opening, then I am under this category, buildings with dominant openings. And I have to refer to this clause in order to find the internal pressure coefficient. And it's going to be a fraction of the average external pressure. I already calculated the external pressure, and it's going to be like 75% to 90% of the external pressure. Right, you have to refer to table 17 in order to find this internal pressure. Anyways, as I said, most engineers, to be very conservative, go for the internal pressure coefficient as positive 0.2 and a negative 0.3. Right, now as I have done it before, we consider the two cases, the 0 degree wind direction and the 90 degree wind direction. For both cases, okay, if I'm considering the 0 or the 90, you have to consider both the values. What that means is, this is for the 0 wind direction, okay, the external pressure for the vertical walls as well as the roof. Now I have to consider the sum, okay, when calculating the net surface pressure. I'll have to do it once for the positive pressure, CPI internal positive pressure as 0.2. This is called case 1. And the case 2, where I do it with the negative value of the internal pressure coefficient. Okay? And then for the 90 degree wind direction, I'll have to do it twice as well. So we go for the positive and then we go for the negative. This is called the case 3 and this is called the case 4. Alright, that makes it. And for the next part, we're going to calculate the internal pressure and the external pressure, and then we're going to find out the net surface pressure on our industrial portal frame. Thank you very much for watching, and I'll see you very soon.